All right, so we went back, we looked at series circuits and calculating the impedance of a series circuit, and a series RL circuit is the one that we used as an example. All right, now we're going to talk about a formula for parallel circuits. Okay, so when we're doing a parallel circuit, which when you build those circuits, the difference is you see over here, I had these two in series. Now another way of representing this is to take one of these banks and then jump it over to this bank that's already in parallel, and that's what I mean, the difference in that RL circuit being series versus parallel is just how you're wiring it up. All right? And so in a parallel circuit, the formula is no longer the triangular formula. All right? The book takes you to a formula that me personally, I've never seen it anywhere else but the book, but I spent some time looking in, and it somehow correlates to a calculus derivative of how you get impedance through a very deep, dark science hole. So I would just say trust it. There's another variant of the formula that you can use, and you can compare the two, and you can see, or you can trust it. It's kind of up to you. In a parallel circuit, a parallel RC, RL, or RLC circuit, and you want to find the impedance, just like we did over there, 1 over Z, oh, no, I'm telling you the other one, hold on, Z equals R X over the square root of R squared plus X squared. Now again, that X is going to be whatever the delta is between the capacitance and the inductive reactance. Okay, so when I see that you see the X in there, that you're just talking about a delta. All right. Now this is how we're going to calculate that. All right. So let's create it. First and foremost, let's calculate it on the board. I'm going to set up a circuit. I'm going to say 124. What do we keep getting 124? Is that what it is? Okay. 124. I'm going to go over here to a 300 ohm resistor, and then over here I'm going to put, let's say, J300 for a 300 ohm inductor. Okay? All right. So based on what I told you there, what should the impedance be of this circuit? Unless you can do square roots really good in your head, you should probably make your calculators move to give me the answer.
What are the numbers?
Do what?
We can't really see the orange.
300 and 300. All the numbers are 300. Let me get a different color for you then. Do what?
Trying to find the angle?
No, the impedance, which is the total opposition taking into account the reactance and the resistance. Can you guys see that formula up there? Is it muddled for you? Is that better? Is that what you got?
12.1.
What is it?
212.1.
212.1? You don't look confident. Did everybody else get 212?
212.1.
What did you get, Golich? I saw you shaking your head. What did you get? Or do can you not see the formula?
No, I can see it.
So punch in 300 times 300,
Got that.
and then divide that by the quantity of 300 squared plus 300 squared, square root that, close your brackets, hit equals. R times X. Rx means R times X.
I thought it was R sub X.
Okay, I'm sorry. I implied that we were there. So R times X.
Yes, that's what I got.
What are we at?
212. Yeah, 212.
212.
Yeah, 12.
Okay, so Z equals 212 ohms. Okay, so with 124 volts, what should our IS be? What is it?
0.58.
Is that right? All right. Before we do all this, let me verify with my calculator. Did I leave it back there, Mike? All right. Divided by the square root of 300 squared plus 300 squared equals 212. Now we're going to say 124 divided by the answer. 0.58. We'll say 0.58. That's what we got. Amps. All right. Can I get a helper? Who wants to build this for me? Don't everybody jump up at once excited. Mr. Miller, thank you. Thank you, sir. That, yeah. You can grab some of those, or you ask me, I'll hand you some. Yes. $300. We're doing that one over there. So it's just 300. So just the first switch on both of them. Back to home. Yep. Parallel inductor off of that. That should be it. Okay. Cool. Well, let's measure our source voltage too. Here, I got two more here, so go ahead and run E1. Mm-hmm. No, that's going to be the resistance. That's going to be the voltage across there. I mean, it should be the same on them because it's a parallel circuit. So I don't have one of those. You got to get one over here. All right, cool. So we set up kind of, it's the same circuit we had before, except now, go ahead, you can stay up here. I want you to flip some switches for me. You tie it, you ride it. You guys been to any kind of rappelling thing? You heard that before? You tie your Swiss seat, you tie it, you ride it. You guys know what a Swiss seat is? It's a very uncomfortable wrap apparatus. Yeah. All right. Go ahead and power it up. Let's see what we're doing. Dial up the voltage. All right. So, is it as expected? Let's look at our results. Tell me the results that we're seeing on the screen up here. Is it as expected? What about the angular relationships going on right now? So here's kind of a difference too. They say that on this phasor diagram, in a parallel circuit, what is consistent across all branches? The voltage. So we use voltage as the reference in the parallel circuit. Now again, you don't have to as far as how you're analyzing. It just depends on what you're trying to do, right? Some of the questions will ask you if you're, some of them trickier word questions, you've seen them before, which one you're using the reference, but that same relationship should exist. So I'm going to change this reference to E1, right? Okay, so now I'm using voltage as my reference.
Okay.
All right. The voltage is doing what to the current? It's leading the current. Okay. So my I sub S here is a result of two different currents going through that circuit, right? We got the current that's going through the branch that has a resistor and the current that's going through the branch that has the inductor, right? And just like we showed with that voltage problem before, that the mathematical sums of those didn't come out perfectly to what the source was, like we did with Kirchhoff's voltage law, because we have different angles, okay? I didn't set it up like this, but the same thing can be said. So just from visually looking at this, does this confirm that?
Yes.
Yeah?
Yes, it does.
Okay, so a lot of these, you see me doing like the math here, and we do this right here, and the idea is just like you're doing in the labs. You kind of seeing this stuff on paper, and then you go build it in the lab, and you build it in the lab, you measure it, you play around with it. I think Mr. Sepulveda told me yesterday, he's like, well, I don't get to play around with it like he was seeing me play around with it. And you absolutely can, but when I say play around with it, I mean vary your stuff. Like you see me come over here, maybe the lab doesn't say to do this, and watch what happens. But it kind of helps you understand that linear relationship going on in there when you do that, right? Right? We're seeing magnitudes change of vectors, and now at the exact same moment I'm seeing that sine wave drop. I'm seeing a vector get longer, shorter, right? Okay. All right. So one other thing that the Lab 5-3 is going to take you through, and one other variant formula, thank you, Mr. Miller, is when we did the arctan to get the phase angle on a series circuit for the phase angle of impedance, we just used arctan of, I want to say, x sub whatever over r, right? Okay. The book shows a formula deep in one of those lines that for the parallel circuit, you're going to use the opposite. You're going to use the arctan of r over x. Okay? Arctan of r over x. There's some explanation behind that, but it's kind of, it's out there. Do you guys see what I'm talking about?
What was it again?
Let's find the page.
It's slide 46.
Is it?
I don't know the page.
Hey, this is one of the labs. I do want to encourage you. Look in the hard copy books. Over this online one, I was looking at something yesterday and saw that one of them, I don't know, 5.1, 5.2, I can't remember which one it was, seemed like it was cut really short in comparison to what was actually in the hard copy book. Now, I don't remember which one it was. I just remember thinking that. So, and plus, we found a lot of errors in the lab on that other one, on the inductance lab too. So, please look at these. I think between 5 and 6 is when the book started getting a little varied. So please take a look at those. Okay. All right. So, do we kind of have a good understanding of what's going on with these vectors and how we're kind of getting resultant vectors and why we're getting resultant vectors? Who has some questions about it? That's what I want to know. Okay? We can talk all day and I can run you through examples of the formula and we can build a bunch of different circuits. But what are your questions? Like, what do you not understand about this? Or what do we need to conceptualize more or work out? Or, hey, does anybody want to come up, build something, calculate something, and let's talk about it? Yes?
So I have two things of noticing this, and I guess the first one is with inductance, it really affecting the current more, because that's where the opposition is. So, because we haven't really talked about anything capacitive. So, that would be the variance there, is if we're working with capacitors, it's going to vary the voltage as opposed to the current.
Well, I think by definition, and this is kind of going down a rabbit hole, by definition, a capacitor opposes changes in voltage and an inductor opposes changes in current, kind of in the characteristic of inductance versus capacitance. But you're saying what now? Ask that question again.
Those were capacitors right now. It would be affecting the voltage more so. The phase angle of the voltage.
You want to build it and test it?
Absolutely. And
Let's
then
do it. Come on.
And then also
It's exploratory learning. It's kind of the whole point of the lab volt
and
system.
then on the tests, because we weren't really working with the vectors a lot, on the test when it was explaining the difference between the phase angle relationship on these, and then it would say, because this right now is negative 40, and on the test there were negative options, but it was based off of which one's your reference.
Mm-hmm.
Every time we went over it, the explanation was always done on the positive side, as opposed to saying, like, here's the beginning of a phase, and it's negative 40, because if you were to find the current, you would have to go into the negative. We never really covered going down into the negative, and that's why the phase angle relationship is negative on that. We just didn't really talk about that as far as one of the answers on the test.
If you pull up the question, we can talk specifics to it. Like I don't conceptualize I don't conceptualize myself personally the drop down method on that, like whatever you just said. I think through it a different way, but that doesn't mean that's wrong. It's just different. So if you bring that question and show me the question, we can talk over that question. But go ahead and turn our power off. Add a capacitor in series there, or I mean in parallel, and you turn the inductor off and kind of play around with it. While he's doing that, what's your questions, Gulich? I need questions from you, man. If you're gonna be the distinguished honor graduate and you get all these gold stars, I need some more questions.
I mean, just, I don't know what I'm looking at. I mean, just look at that vector you had up. I can see that voltage is the reference. That's zero. Your current. Was lagging. But I mean, where you talking about phase angles and all that?
Okay, so you said it was lagging, right? You saw that the current was lagging the voltage in there,
Yeah.
right? And the Eli Ice thing that kind of confirms it, right? Because that was an inductive circuit, right? It had resistance in it, but you know it was an RL circuit, which means it's not going to be in perfect unity. There is going to be a phase angle. There's two kids pulling at this point, and it's pulling in that lagging direction. The current lagging the voltage, right? Voltage leading the current in that capacitive circuit. So that phase angle that we're talking about, or a phase angle, depending on what we're referencing, is the angle from that zero mark of whatever that resultant vector is that we're looking at. All right, so again, if I'm being pulled down the aisle this way, I start getting pulled this way, right? So I'm starting to lag because of the direction that this kid's pulling. He's lagging me, right? I'm going this way. Well, I'm going to end up, logic, I'm going to end up going in some angle, right? I'm not going to end up going straight. I'm not going to end up going that way. I'm going to end up at that angle. What is that angle that I'm actually going from the reference, right? That's the phase angle. And you're seeing that in this phasor diagram.
We're seeing it, but we're just not.
You're not doing anything with it yet because the lab is going to run you through, it's going to ask you some questions. What is the phase angle? It's going to run you through some crazy circular stuff where you're going to see a phase angle up there. You're probably already going to know it. You're going to do like Mr. Hill did and maybe read it off the bottom of the screen, right, if you see the readout in there. And then it's going to have you, okay, do the arctangent of this, and you're not going to know why. That's why I try to tell you ahead of time why. Then it's going to say, okay, we'll do this. And you go, why? Right? And all it's going to do is circle back to go, oh, man, aha, I see what it did there. I just did a bunch of different calculations to come back to that. It's the same thing as all the labs.
Well, that's what I was trying to figure out when we're doing these equations for just to find the amps.
I'm finding the amps on the board because in my head, it was just a good reference point because I have I1 displayed up there just to confirm some stuff. That's really why I picked that.
Okay.
I think you need to play around with it. I think that's what needs to happen. We need to do labs with you, and we can play around with it. All right, so go ahead. Hot it up. Let's see. So what are we expecting? What are you expecting? Absolutely.
So the difference isn't necessarily different because of one being in opposition to another. It's just which one you're using as a reference.
Yes, but in a sense, let's do this. Let's take these. Now add that inductor bank parallel to that capacitor bank, which is parallel to that resistive bank. Now, whoa, is that the same one?
No.
Oh, okay. Scared me. Is that what's expected?
Yes.
And now flip off this one, right? I'll flip up. And we're seeing that jump back and forth, right? Now pay attention to those vectors that you're seeing up to the reference vector, because we have it reference off source right now, right? Everything's off source, okay? So is our source voltage changing as a result of this?
No.
I mean, in the grand scheme of things, is that the source voltage was the source voltage? Well, what is changing, though, is the current. All right, and you can see those minute shifts in the magnitude of that current vector. And so one of the things that it talks about in one of these labs is power factor correction. And power factor correction is still trying to get the same amount of P out there for the load, but minimizing the actual line current that's out there. And you're minimizing the line current because you're bringing that phase angle as close to 1 as you can, which is thereby reducing, all right? You are not creating such a long hypotenuse. That makes sense? And so like, we think about the distribution system, and we're going to talk about this when you get into the components of distribution block, and I kind of hinted at it the other day. I don't know why I'm holding this microphone. The power companies, in order for power factor correction, because inductance is that phenomenon that's happening, all throughout the world, that they add deliberate design capacitor banks out there to the system so it can do just that. It can do exactly the equivalent of I'm up here with my load here. All right, let me turn this off. I got all this inductance out here. All right, and right now I'm at a pretty sharp angle right there. So if we were to do the what is that, the 45, right? So that's not the most effective system by the time we ran the math all the way out. Okay? That's not going to be, there's going to be a pretty big difference there between the S and the P, right? But the moment I add the same amount, or let's just say some fractional amount of capacitance, not only did I shorten my current vector, but I brought it a lot closer in phase relationship back to that reference, which is thereby reducing the phase angle between voltage and current, which is then in turn going to reduce that line current. Make sense? Good to go?
When you said reduce the line current, what was that?
What the source current, the overall system current. And so we're visualizing that here because we're monitoring I mean, we could hook a bunch more voltmeters, and you kind of saw me do it yesterday in the demonstration. Hook up the different channels, E1, E2, E3, across each one of those, the R, the L, the C, and then go back. Here I'm just looking at source. So you're seeing directly how does the system, and by system we could take this and we could change this to, we could say that this is the generator, right? And now we're measuring what the generator sees, even though out here we've got this stuff going on the load, right? And the load is moving us inductive. We've got motors and stuff and transformers out there and all kinds of stuff. It's this inductance is happening, but it's getting a little intense. We want to limit that line current down so we can deliberately change how we tip that beer mug and fill that beer mug up, right? To get more beer, less foam. Good? All right. So who's like just crazy confused? Would you call yourself crazy confused? I don't think you are. Good. Slightly confused where you need to be. Because again, this is a tit for tat thing, right? You get the lecture and then you go play around with it. You do some calculations. That's why I try to get you to use the calculations yourself on your computer. Because you can north-south me all day and just say things. But if you're not going through the motions, it doesn't click, right? So again, going through the lab, you're going to do the calcs and it should start to click as you're getting these results. And when it doesn't click and you get frustrated, and you want to keep calculating and trying to figure out, that's actually where you learn the most, right? Last night at this, I do a robotics program for the local, for my kids' school, and the middle school team is building this competition robot last night, and they kept putting this piece together wrong. They kept doing it. I didn't tell them they were doing it wrong. They kept figuring it out that they were doing it wrong. And so for an hour and a half, they kept putting it on, taking it off, putting it on, taking it off. Until finally they got it on right where it was. And one of the kids was like, man, I know this part up and down. Now, why does he know the part up and down? Because he was frustrated and he just kept going and it kept messing up until it, aha. The lab is the aha from this. So if you're still slightly confused, good, awesome. Let's go over here, let's build some stuff, let's play around, let's do some calculations, and let's argue. I didn't tell you this about me and my intro. I absolutely love to argue. I absolutely love to argue. So please, somebody's going to learn. You might be right, I might be wrong. I don't think so, but I might be wrong, right? Somebody's going to see, right? Love to argue, okay? But that's how people learn. I think I've learned like 90% of Army stuff from arguing with people, and then people get mad and go look it up and figure it out, right? So, we good? All right, let's do some labs.